Hello, viewers from AraaTech. Let's start our new topic large language model. Artificial intelligence is a captivating field focused on empowering machines to emulate human thinking and learning processes. The essence lies in developing intelligent computers capable of performing tasks without explicit programming, relying on the ability to learn from experiences. While the roots of artificial intelligence date back to the mid 20th century, recent decades have witnessed remarkable progress. Artificial intelligence can be broadly classified into two categories: narrow artificial intelligence and general artificial intelligence. Narrow artificial intelligence is tailored for specific tasks such as voice recognition, while general artificial intelligence possesses the ability to comprehend, learn, and apply knowledge across diverse domains. The scope of artificial intelligence includes machine learning, where computers glean patterns from data, and deep learning, a subset utilizing neural networks to replicate the intricacies of the human brain. This multidimensional approach underscores the vast potential and versatility of artificial intelligence in transforming how machines interact with and adapt to the world. History: the concept of artificial intelligence was first introduced in 1950 with pioneers like Alan Turing laying the groundwork. Over the years, artificial intelligence has evolved through different phases, experiencing both periods of growth and AI winters. When progress slowed, recent breakthroughs in algorithms, computing powers, and data availability have fueled the artificial intelligence renaissance we are witnessing today. Applications: artificial intelligence is everywhere in our daily lives, from virtual assistants like Siri and Alexa, understanding and responding to our voice commands, to recommendation systems suggesting movies on streaming platforms. Artificial intelligence is enhancing convenience and efficiency. In healthcare, artificial intelligence aids in diagnostics and in finance. It powers fraud detection systems. Understanding the history and applications of artificial intelligence sets the stage for exploring its diverse and exciting aspects. Machine learning basics. Machine learning is a powerful aspect of artificial intelligence that allows computers to learn from data and improve their performance over time without being explicit programmed. There are two main types of machine learning: supervised learning and unsupervised learning. Supervised learning. In supervised learning, the computer is provided with labeled data input along with the corresponding correct output. The algorithm learns to map the input data to the correct output by making predictions and adjusting its parameters. It's like teaching a computer by example. For instance, if you are training a model to recognize cats and dogs, you would show it pictures of cats and dogs with labels, and the model learns to distinguish between them. Unsupervised learning. Unsupervised learning, on the other hand, deals with unlabeled data. The algorithm explores the data's structure and finds patterns without specific guidance. It's like discovering hidden relationships within the data. An example is clustering, where the algorithm groups similar data points together. If you have a collection of news articles and want to find topics without predefined categories, unsupervised learning can help identify natural groupings. Everyday examples: spam filter, supervised learning. Think of your email spam filter. It learns from your marked emails, spam or not, to predict and filter out unwanted emails in the future. Recommendation systems, collaborative filtering, unsupervised learning. Platforms like Netflix use unsupervised learning to recommend movies. The algorithm finds patterns in user behavior and suggests movies similar to what you have watched. Understanding these basics opens the door to a wide array of machine learning applications that impact our daily lives. Linear algebra for machine learning. Linear algebra is a fundamental mathematical tool that plays a crucial role in machine learning. It deals with vectors, matrices, and their operations. Let's break down these key concepts. Vectors. A vector is an array of numbers in machine learning. It often represents a set of features for a data point. For example, if you are working with houses, a vector could represent features like square footage, number of bedrooms, and bathrooms. Matrices. A matrix is a two-dimensional array of numbers. It's like a table of data. Each row can represent a different data point and each column can represent a different feature. Matrices are used to store and manipulate datasets in machine learning. Operations. Linear algebra involves operations like addition, subtraction, and multiplication in machine learning. These operations are used to transform and analyze data. For instance, multiplying a matrix by a vector can be used to apply a set of weights to features. Everyday example. Imagine you have data on houses with features like square footage, number of bedrooms, and price. You could represent each house as a vector and organize all the houses in a matrix. If you want to predict the price, you might use linear algebra operations to adjust the weights of each feature to find the best fit for your model. Linear algebra is the backbone that allows machines to process and understand these mathematical operations efficiently. Calculus for machine learning. Calculus is another essential branch of mathematics that finds extensive use in machine learning, particularly in the optimization processes that enable models to learn and improve. Two key concepts from calculus that are crucial in machine learning are derivatives and gradients. Derivatives. A derivative measures how a function changes as its input changes. In the context of machine learning, derivatives are used to find the rate of change of a model's output concerning its parameters. This is crucial for understanding how tweaking parameters can affect the model's performance. Gradients. The gradients is a vector of all the partial derivatives of a function. In machine learning, this vector points in the direction of the steepest increase in the function. Gradients are extensively used in optimization algorithms to adjust the parameters of a model during training, aiming to minimize the difference between predicted and actual outcomes. Everyday example. Think of a mountainous landscape as a metaphor for a mathematical function. The slope of the terrain at any point corresponds to the derivative. If you are standing on a hill, the steepest direction you could descend represent the gradient. In machine learning, the optimization process is like finding the lowest point in this landscape to achieve the best model performance. Calculus provides the mathematical tools to navigate and reach this optimal point efficiently. Probability and statistics. Probability. Probability deals with the likelihood of events occurring. In machine learning, it helps quantify uncertainty and randomness. For example, in a spam filter, probabilities is used to assess the likelihood that an email is spam based on certain features. Statistics. Statistics involves collecting, analyzing, interpreting, presenting, and organizing data. In machine learning, statistical methods help draw meaningful insights from data, from identifying patterns to making predictions. For instance, in medical diagnosis, statistics are used to assess the accuracy of a diagnostic model. Foundations for understanding uncertainty. Probability is a powerful tool for dealing with uncertainty. It allows machine learning models to express the likelihood of different outcomes, helping them make more informed decisions. Understanding uncertainty is crucial in scenarios where predictions are not always certain, such as weather forecasting or stock market predictions. Data distribution, statistics, particularly concepts like mean, median, and standard deviation, help describe the distribution of data. Knowing how data is distributed is essential for building accurate models. For instance, in predicting exam scores, understanding the distribution of past scores helps set realistic expectations for future predictions. Everyday example, consider weather forecasts. When a meteorologist predicts a 70% chance of rain, they are using probability. This is based on statistical analysis of past weather patterns, helping them estimate the likelihood of rain on a given day. Probability and statistics similarly empower machine learning models to make predictions and decisions in the face of uncertainty. Python programming. Python is the go-to programming language in the field of artificial intelligence due to its simplicity, readability, and extensive libraries. Here is an overview of why Python is essential for artificial intelligence and its basics. Why Python in artificial intelligence? Python is widely used in artificial intelligence for several reasons. It has a large and active community, making it easy to find resources and support. Its syntax is clear and concise, facilitating rapid development. Moreover, Python has extensive libraries like NumPy, TensorFlow, and PyTorch, making it a preferred choice for artificial intelligence and machine learning projects. Basics of Python. Python is known for its readability and ease of use. Key concepts include variables, data types, integers, floats, strings, control flow structures, if statements, loops, and functions. Understanding these basics is crucial for writing artificial intelligence algorithms and implementing machine learning models. Everyday example. Imagine you are a chef, programmer, in a kitchen coding environment, and Python is your set of well organized kitchen tools. You use simple instructions, Python code, to create a delicious dish, artificial intelligence application. Python's readability and simplicity make it like having a recipe book that anyone can follow, whether you are slicing data or mixing algorithms. Python is the versatile chef's knife in your artificial intelligence kitchen. NumPy and Pandas. NumPy and Pandas are powerhouse libraries in Python that play crucial roles in handling and manipulating data for artificial intelligence and machine learning applications. NumPy. Purpose. NumPy provides support for large multi-dimensional arrays and matrices along with mathematical functions to operate on these arrays efficiently. Daily life analogy. Think of a spreadsheet where you organize data in rows and columns. NumPy is like having a supercharged version of this spreadsheet in Python. For example, if you are working with a data set of house prices, NumPy allows you to perform quick calculations on the entire data set, such as finding the average price or identifying the highest priced house. Pandas. Purpose. Pandas offers data structures like data frame for efficient data manipulation and analysis. It is especially useful for handling labeled and structured data. Daily life analogy. Imagine you have a library of books where each book has details like title, author, and genre. Panda is like a magic librarian for your data. It helps you easily filter out books by specific author, sort them by publication date, or even group them by genre. In the same way, Pandas empower you to explore and manipulate your data effortlessly. Everyday example. Consider a situation where you have a list of expenses, amount, category, date, recorded in a spreadsheet. NumPy allows you to perform operations like calculating the total expense or finding the average amount. Pandas, on the other hand, helps you organize this data like a pro, allowing you to quickly find all expenses in a certain category, summarize spending by month, or even analyze trends over time. These libraries make data manipulation in Python feel like navigating through a familiar and efficient data landscape. Data visualization. Data visualization is a crucial aspect of understanding and communicating patterns and insights within data. Matplotlib and Seaborn are powerful tools in Python for creating compelling visual representations. Matplotlib. Purpose. Matplotlib is a versatile plotting library that allows the creation of various types of charts, plots, and graphs. It provides fine grained control over every aspect of a plot. Daily life analogy. Imagine you are telling a story and you want to draw a diagram to explain a concept. Matplotlib is like having a toolkit with different drawing instruments, pencils, pens, and markers. It allows you to create visual aids tailored to your storytelling needs. Seaborn. Purpose. Seaborn is built on top of Matplotlib and provides a high-level interface for creating attractive and informative statistical graphics. Daily life analogy. If Matplotlib is your toolkit, Seaborn is like having a set of pre-designed templates for specific types of stories. It simplifies the process of creating aesthetically pleasing and informative visualizations. For example, if you have a dataset of house prices and want to visualize the distribution, Seaborn can help you create a beautiful histogram with just a few lines of code. Everyday example. Consider a dataset showing the monthly sales of a store. Matplotlib can help you create a line chart to visualize the sales trend over time. Now, if you want to add more style and context, Seaborn comes in handy. With Seaborn, you can easily enhance the same chart by adding color, adjusting the AXIs, labels, and incorporating statistical elements, making your sales trend more visually appealing and insightful. These tools turn raw data into visual stories that are easy to interpret and share. Supervised learning. Supervised learning is a paradigm in machine learning where the algorithm is trained on a labeled dataset, meaning the input data is paired with corresponding output labels. It involves crucial concepts of training, testing, and validation. Training. Purpose. During the training phase, the algorithm learns to map input data to correct output labels. It adjusts its internal parameters based on the provided labeled examples. Daily life analogy. Think of teaching a dog new tricks. You show the dog a trick input, and when it performs correctly, you reward it. Output label. Through repetition, the dog learns to associate specific actions with rewards. Similarly, in supervised learning, the algorithm learns by being exposed to labeled examples. Testing. Purpose. Once trained, the model needs to be tested on new unseen data to evaluate its performance and generalization ability. Daily life analogy. Imagine you have taught your dog several tricks and now you want to see if it can perform a new trick it has never seen before. Testing in machine learning is akin to presenting the model with new unseen data and assessing how well it predicts the correct outcomes. Validation. Purpose. Validation is an intermediate step between training and testing. It involves tuning the model's hyperparameters to achieve optimal performance. Daily life analogy. Going back to the dog analogy, before a big show, you might fine tune the way you command or reward the dog to ensure it performs at its best. Similarly, in machine learning, validation is the process of adjusting the model's setting to enhance its overall performance. Everyday example. Consider a spam filter. During training, the algorithm is fed with emails labeled as either spam or not spam. It learns to recognize patterns associated with spammy content. After training, it's tested on a new set of emails it has never seen to assess how well it generalizes to distinguish between spam and legitimate emails. Validation could involve tweaking parameters such as adjusting the sensitivity of the filter to achieve the best balance between catching spam and avoiding false positives. Unsupervised learning. Unsupervised learning is a branch of machine learning where the algorithm is given unlabeled data and must find patterns or relationships within it. Key concepts in unsupervised learning include clustering, dimensionality, reduction, and association. Clustering. Purpose. Clustering involves grouping similar data points together based on certain features or characteristics. It's like discovering natural deviance within the data without predefined categories. Examples. Imagine you have a basket of mixed fruits and you want to organize them. Clustering would involve grouping similar fruits together, like putting all the apples in one group, oranges in another, and so on. Dimensionality reduction. Purpose. Dimensionality reduction aims to simplify complex data by reducing the number of features while preserving important information. It helps in visualizing and processing data more efficiently. Example. Think of a detailed map with numerous data points. If you want to highlight major cities without losing essential geographical information, dimensionality reduction is like creating a simplified version of the map with only key locations. Association. Purpose. Association involves discovering relationships or connections between variables in a dataset. It identifies patterns such as items that frequently appear together. Example. In a supermarket, association analysis might reveal that customers who buy bread are also likely to buy butter. This information can be valuable for marketing or product placement strategies. Everyday example. Consider a social network where users are connected based on their interactions. Unsupervised learning could be applied to identify communities or groups of users who share common interests. Clustering would help group users with similar behavior. Dimensionality reduction might simplify the representation of user profiles, and association analysis could reveal patterns like users who frequently interact with each other. These unsupervised learning techniques uncover hidden structures within the data, providing valuable insights. Neural networks. Neural networks are a fundamental concept in artificial intelligence and machine learning. Modeled after the human brain, they consist of interconnected nodes, neurons, organized into layers. Here are the basics of artificial neural networks. Neurons and layers. Neurons. Neurons are the basic units of a neural network. Each neuron receives input, processes it using weights, applies an activation function, and produces an output. Layers. Neurons are organized into layers. The input layers receives data, the hidden layers process it, and the output layer produces the final result. Weights and activation functions. Weights. Neurons are connected by weights, representing the strength of connections. These weights are adjusted during training to optimize the network's performance. Activation functions. Neurons use activation functions to introduce non-linearity into the network. Common activation functions include sigmoid, TANH, and ReLU. Feed forward and back propagation. Feed forward. In the feed forward phase, data passes through the network layer by layer, production and output. This is the process of making predictions. Backpropagation. Backpropagation is the training phase. It involves comparing the predicted output with the actual output, calculating the error, and adjusting weights backward through the network to minimize error. Loss function. The loss function measures the difference between the predicted output and the actual output. The goal during training is to minimize this loss. Training and learning. Neural networks learn by adjusting weights during training. Through iterations, the network improves its ability to make accurate predictions. Everyday example. Consider training a neural network to recognize handwritten digits. The input layer receives pixel values of an image. Hidden layer processes this information and the output layer predicts the digit 0 to 9. During training, the network adjusts its weights based on the difference between predicted and actual digits, gradually improving its accuracy. This process is analogous to teaching a computer to recognize handwriting through example. Deep learning. Deep learning is a subset of machine learning that focuses on neural networks with multiple layers, also known as deep neural networks. Here is an overview of deep learning and its key components. Deep neural networks, DNNs. Deep learning involves using neural networks with many hidden layers. These networks can automatically learn hierarchical representations of data, capturing intricate patterns and features. Architectures. Convolutional neural networks, CNNs, well suited for image-related tasks. CNNs use convolutional layers to detect patterns like edges and textures. Recurrent neural networks, RNNs, effective for sequence data. RNNs have connections that form cycles, allowing them to capture dependencies over time. Long short-term memory, LSTM networks, a type of RNNA. LSTMs are designed to overcome the vanishing gradient problem and are useful in tasks requiring memory of past events. Generative adversarial networks, GANs, comprising a generator and a discriminator. GANs are used for generating new data instances such as images. Feature learning. Deep learning excels at automatically learning hierarchical features from raw data. Each layer in a deep network extracts progressively more abstract features, allowing the model to understand complex relationships. Training challenges. Training deep networks can be challenging due to issues like vanishing or exploding gradients. Techniques like batch, normalization, and careful weight initialization help address these challenges. Transfer learning. Transfer learning involves using a pre-trained deep learning model on a similar task before fine-tuning it on the specific task of interest. This approach is valuable when labeled data is limited. Everyday example. Consider using deep learning for image recognition. A deep neural network like a CNN can be trained to recognize objects in images. As the network learns, lower layer might detect simple features like edges, while higher layers combine these features to recognize complex objects. This process mimics how the human brain processes visual information, making deep learning powerful for tasks like image and speech recognition. Convolutional neural networks, CNNs. Convolutional neural networks, CNNs, are specialized deep learning architectures designed for tasks involving image analysis and recognition. Here is a detailed exploration of CNNs. Convolutional layers. CNNs use convolutional layers to automatically and adaptively learn special hierarchies of features from input images. Convolutional involves sliding a filter, also called a kernel, across the image, capturing local patterns and special relationships. Pooling layer. Pooling layers, typically max pooling, follow convolutional layers to downsample the special dimensions of the learned features. This reduces computational complexity and focuses on the most essential information. Activation functions. Activation functions like ReLU, rectified linear unit, introduce non-linearity, enabling the model to learn complex patterns. ReLU, for example, replaces negative values with zero. Fully connected layers. After several convolutional and pooling layers, CNNs often have one or more fully connected layers for making predictions. These layers connect every neuron to every neuron in the preceding and succeeding layers. Parameter sharing. CNNs leverage parameter sharing, meaning the same filter is applied to multiple positions in the input. This reduces the number of parameters and enhances the model's ability to generalize. Hierarchy of features. CNNs automatically learn hierarchical representations of features. Lower layers may capture simple features like edges, while higher layers combine these features to recognize complex patterns and objects. Transfer learning. CNNs are often pre-trained on large datasets, that is, ImageNet, and fine-tuned for specific tasks. This transfer learning approach helps achieve better performance, especially when labeled data is limited. Everyday example. Think of a CNN as an intelligent artist examining an image canvas. The artist uses specialized brushes, convolutional layers, to detect different aspects like edges, textures, and colors. After each stroke, they step back, pooling layers to get a holistic view. As they paint layer by layer, they gradually recognize intricate details and ultimately identify the entire scene. Similarly, CNNs discern features in images through layers, capturing complex patterns for tasks like object recognition or facial analysis. Recurrent neural networks (RNNs). Recurrent neural networks (RNNs) are specialized architectures within the realm of deep learning designed for processing sequential data. Here is a comprehensive look at RNNs. Sequential processing. RNNs are tailored for tasks where the order of data points matters. Unlike traditional feed-forward networks, RNNs maintain a hidden state that captures information from previous inputs, allowing them to consider context and dependencies in sequential data. Recurrent connections. The defining feature of RNNs is their recurrent connections. Each node in the network has a connection to itself, allowing information to persist and flow through the network over time. Time steps. RNNs process data in a sequential manner, treating each element of the sequence as a distinct time step. This makes them suitable for tasks like time series analysis, natural language processing, and speech recognition. Hidden state. The hidden state of an RNN serves as its memory, capturing information from previous time steps. This hidden state evolves as the network processes each element in the sequence. Vanishing gradient problem. RNNs can face the vanishing gradient problem, where the influence of early time steps diminishes during training. Long sequences may lead to difficulties in capturing long-term dependencies. Long short-term memory (LSTM). To address the vanishing gradient problem (LSTM), networks were introduced. LSTMs have a more sophisticated memory cell that can selectively store, read, and erase information, allowing them to capture long-range dependencies. Applications. RNNs find applications in various domains, including natural language processing for language modeling and translation, speech recognition, and predicting time series data. Everyday example. Consider predicting the next word in a sentence. An RNN processes words one by one, maintaining a hidden state that encapsulated the context of previous words. It's like reading a sentence and understanding the context to predict the next word accurately. In this way, RNNs excel in tasks where the order of information is crucial for making predictions or generating sequences. Natural language processing (NLP). Natural language processing is a branch of artificial intelligence focused on enabling machines to understand, interpret, and generate human language. Here is an in-depth exploration of NLP. Tokenization definition. Tokenization involves breaking down a text into a smaller units, usually words or subwords. It's the first step in understanding the structure of a sentence. Example: the sentence, "The quick brown fox jumps over the lazy dog," would be tokenized into individual words. The quick brown fox jumps over the lazy dog. Part of speech tagging (POS). Definition: POS tagging assigns grammatical categories, nouns, verbs, adjectives, etc. to each word in a sentence. Example: in the sentence "She is reading a book," POS tagging would label "she" as a pronoun, "is" as a verb, "reading" as a verb, "a" as an article, and "book" as a noun. Named entity recognition (NER). Definition: NER identifies and classifies entities such as names of people, organizations, locations in a text. Example: in the sentence "Apple Incorporation Inc. is located in Cupertino," NER would recognize Apple Inc. as an organization and Cupertino as a location. Word embeddings. Definition: word embeddings represent words as dense vectors in a continuous vector space. They capture semantic relationships between words. Example: the vectors for king and queen might be closer in the embedding space compared to king and car. Sentiment analysis. Definition: sentiment analysis determines the sentiment expressed in a piece of text, such as positive, negative, or neutral. Example: analyzing product reviews to determine customer sentiments, that is, "I love this product," is positive. Machine translation. Definition: machine translation involves automatically translating text from one language to another. Example: translating an English sentence like "Hello, how are you?" to French as "Bonjour," comment CAVA. Chatbots and dialogue systems. Definition: NLP is crucial in developing chatbots and dialogue systems that can understand and respond to natural language queries. Example: a chatbot helping users with customer support inquiries or answering general questions. Everyday example: imagine using a voice activated virtual assistant. NLP enables it to understand your spoken commands, extract relevant information, and respond appropriately. From composing email to setting reminders, NLP empowers machines to comprehend and generate human-like language, making interactions more natural and intuitive. Computer vision. Computer vision is a field of artificial intelligence that enables machines to interpret and make decisions based on visual information. Here is a comprehensive overview of computer vision. Image processing. Definition: image processing involves manipulating and analyzing visual data to enhance or extract useful information. Example: applying filters to improve image quality, removing noise, or detecting edges. Object detection. Definition: object detection involves identifying and locating objects within an image or video. Example: detecting and labeling cars in a traffic scene or locating faces in a group photo. Image classification. Definition: image classification assigns a label or category to an entire image. Example, identifying whether an image contains a cat or a dog. Semantic segmentation definition. Semantic segmentation involves classifying each pixel in an image into specific categories, creating a detailed map of object boundaries. Example, distinguishing between different objects in a scene such as road, buildings, and pedestrians. Object recognition definition. Object recognition goes beyond detection by identifying specific instances of objects. Example, recognizing a particular breed of dog or specific landmarks in an image. Feature extraction definition. Feature extraction involves capturing relevant information from images to represent their key characteristics. Example, extracting texture, color, or shape features to describe objects in an image. 3D reconstruction definition. 3D reconstruction aims to create three-dimensional models of objects or scenes from multiple 2D images. Example, generating a 3D model of a room using photographs taken from different angles. Facial recognition definition. Facial recognition identifies and verifies individuals based on facial features. Example, unlocking smartphones using facial recognition or identifying individuals in a crowd. Everyday example, consider a smart camera that automatically recognizes and tags people in your photo collection. Computer vision algorithms analyze facial features, identify individuals, and group photo based on the people present. This application simplifies organizing and retrieving images, showcasing the practicality and convenience of computer vision in our daily lives. Reinforcement learning. Reinforcement learning (RL) is a type of machine learning paradigm where an agent learns to make decisions by interacting with an environment. The agent receives feedback in the form of rewards or penalties, allowing it to learn optimal strategies through trial and error. Here is a detailed exploration of reinforcement learning. Agent, environment, and actions. Agent, the learner or decision maker interacting with the environment. Environment, the external system with which the agent interacts. Actions, the decisions or moves the agent can make within the environment. States. Reinforcement learning systems operate in different states, representing the current situation or configuration of the environment. Rewards and penalties. The agent receives rewards or penalties based on the actions it takes. The goal is to maximize cumulative rewards over time. Policy. A policy defines the strategy or rules that the agent follows to make decisions in different states. The objective is to learn an optimal policy for maximizing rewards. Exploration and exploitation. Reinforcement learning involves a trade-off between exploration, trying new actions to discover their effects, and exploitation, choosing actions that are known to yield high rewards. Markov decision process and MDP. Reinforcement learning problems are often modeled as Markov decision processes where the future state of the system depends only on the current state and action, not on past events. Value function. The value function estimates the expected cumulative reward for being in a certain state or taking a specific action. It helps the agent evaluate the desirability of different states or actions. Q-learning and deep Q network (DQN). Q-learning is a popular algorithm that estimates the quality of actions in a given state. Deep Q networks use neural networks to approximate the Q values in more complex environments. Applications. Reinforcement learning is applied in various domains such as game playing, that is AlphaGo, robotics, autonomous vehicles, and optimizing business strategies. Everyday example. Think of reinforcement learning as teaching a dog new tricks. The dog, agent, explores different actions, tricks, and receives rewards when it performs well over time. It learns the optimal sequence of actions to maximize rewards. Similarly, reinforcement learning algorithms learn by interacting with an environment, adjusting their strategies based on the outcomes, and gradually improving decision making. Transfer learning. Transfer learning is a machine learning technique where a model trained on one task is adapted for a new related task. Rather than training a model from scratch, knowledge gained from solving one problem is utilized to improve performance on a different but related problem. Here is a detailed exploration of transfer learning. Pre-trained models. Transfer learning often starts with a pre-trained model that has been trained on a large data set for a specific task, such as image classification. Base model and task specific layers. The pre-trained model is composed of a base model which captures general features and task specific layers responsible for the specific predictions of the original task. Fine tuning. The process involves adjusting the parameters of the pre-trained model on the new task's dataset. This can include freezing certain layers to preserve knowledge and only updating specific layers. Domain adaptation. Transfer learning is particularly useful when the source and target tasks have different but related domains. The model adapts its knowledge from the source domain to the target domain. Feature extraction. In some cases, transfer learning involves using the pre-trained model as a feature extractor. The learned features from the base model are used as inputs for a new task specific model. Applications. Transfer learning is widely applied in computer vision, natural language processing, and other domains. For example, a model trained on a large dataset for image recognition can be fine-tuned for a specific application like detecting plant diseases. Benefits. Transfer learning saves computational resources and time compared to training a model from scratch. It is especially valuable when labeled data for the target task is limited. Challenges. Choosing the right pre-trained model, deciding which layers to fine-tune, and handling domain differences are challenges in transfer learning. Everyday example. Imagine you are learning to play a new musical instrument, say the guitar. After already mastering the piano, your understanding of musical concepts, rhythm, and notation transfers to the new instrument. While there are differences between the piano and the guitar, your prior knowledge expedites the learning process. Similarly, transfer learning leverages existing knowledge to accelerate learning on new related tasks in machine learning. Model deployment. Model deployment is the process of taking a trained machine learning model and integrating it into a real world system to make predictions or assist in decision making. Here is a detailed exploration of model deployment. Integration with software systems. Deployed models are integrated into software applications, systems, or platforms to provide predictions or insights. Scalability. Deployed models need to handle varying levels of demand. Scalability ensures that the system can efficiently accommodate an increasing number of requests. APIs, application programming interfaces. Models are often exposed through APIs, allowing other software components to send input data and receive predictions or results. Cloud deployment. Cloud services enable the deployment of models on scalable and reliable infrastructure. Platforms like AWS, Azure, and Google Cloud provide resources for hosting and managing models. Containerization. Containerization tools like Docker simplify the packaging of models and their dependencies, ensuring consistent performance across different environments. Monitoring and logging. Continuous monitoring of model performance and logging of predictions are essential for identifying issues. understanding model behavior, and improving over time. Security considerations. Ensuring the security of deployed models is crucial to protect sensitive data and prevent malicious attacks. Versioning. Version control helps manage different iterations of models. It allows for easy rollback in case of issues and supports the deployment of updated models. Feedback loop. Establishing a feedback loop is important for continuous improvement. Insights gained from model performance in the real world can inform future updates and enhancements. User interface (UI). For models with user interactions, a user-friendly interface is designed to facilitate input, display results, and enhance the overall user experience. Everyday example. Imagine a weather prediction application that uses a machine learning model to forecast local weather conditions. Model deployment in the scenario involves integrating the predictive model into the app infrastructure. User interact with the app, providing location data, and the deployed model delivers real-time weather predictions. This seamless integration of machine learning into practical applications enhances our daily experiences and decision-making processes. Ethics in artificial intelligence. Ethics in artificial intelligence involves understanding and addressing the moral and societal implications of artificial intelligence technologies. It aims to ensure that artificial intelligence is developed, deployed, and used in a responsible and fair manner. Here is a comprehensive exploration of ethics in artificial intelligence. Fairness and bias. Definition. Ensuring that artificial intelligence systems are unbiased and treat individuals fairly, irrespective of their characteristics such as race, gender, or socioeconomic status. Example, preventing facial recognition systems from exhibiting racial bias in identification. Transparency definition, making artificial intelligence systems transparent and understandable, allowing user to comprehend how decisions are made. Example, providing explanations for credit scoring decisions made by artificial intelligence algorithms. Accountability definition, holding individuals, organizations, or algorithms accountable for the consequences of artificial intelligence decisions. Example, establishing responsibility when an autonomous vehicle is involved in an accident. Privacy definition, protecting individuals' privacy by ensuring that artificial intelligence systems handle personal data responsibly and adhere to privacy regulations. Example, implementing privacy preserving techniques in healthcare artificial intelligence to protect patient data. Security definition, safeguarding artificial intelligence systems against malicious attacks and ensuring that they cannot be exploited to cause harm. Example, implementing robust security measures in autonomous systems to prevent unauthorized access. Inclusivity definition, ensuring that artificial intelligence technologies are designed to be accessible and beneficial for diverse populations. Example, developing AI-driven education tools that cater to various learning styles and abilities. Social impact definition, considering and mitigating the broader societal impact of artificial intelligence technologies, both positive and negative. Example, evaluating the effects of artificial intelligence on employment and making measures to address potential job displacement. Bias mitigation definition, implementing strategies to identify and mitigate biases in training data and algorithms to avoid perpetuating societal inequalities. Example, regularly auditing and updating facial recognition models to reduce racial and gender biases. Everyday example, consider a hiring platform that uses artificial intelligence to screen job applications. Ethical considerations would involve ensuring that the algorithm does not discriminate based on gender or race, that the decision-making process is transparent, and that applicants' privacy is protected. Ethical artificial intelligence practices are crucial to building trust in the technology and avoiding unintended negative consequences. Explainable AI, XAI, ensuring artificial intelligence models' decisions are interpretable. Explainable AI focuses on developing and implementing machine learning models that can provide clear and understandable explanations for their decisions. It aims to enhance transparency, trust, and accountability in artificial intelligence systems. Here is an in depth exploration of explainable artificial intelligence. Interpretability definition: the degree to which humans can understand the cause and effect relationships in a model's decision making process. Example: knowing which features were influential in a credit approval decision. Model transparency definition: making the internal workings of artificial intelligence models understandable and accessible to users. Example: providing a breakdown of the factors considered by a medical diagnosis model. Human readable outputs definition: presenting model outputs in a format that is easy for humans to comprehend. Example: expressing the confidence level of a sentiment analysis model in plain language. Local and global explanations definition: offering explanations for individual predictions, local, as well as insights into overall model behavior, global. Example: explaining why a specific image was classified as a cat, local, and highlighting common features in cat images, global. Counterfactual explanations definition: demonstrating how changes in input variables would lead to different model outcomes. Example: showing what modifications to a loan application would have resulted in approval instead of rejection. User-friendly interfaces definition: designing interfaces that present explanations in a clear and accessible manner for users without technical expertise. Example: using visualizations to illustrate the factors influencing a predictive model's decision. Context-aware explanations definition: providing explanations that consider the specific context of the application or user. Example: offering different explanations for a medical diagnosis based on the level of detail required by a healthcare professional versus a patient. Ethical considerations definition: ensuring that explanations do not inadvertently reveal sensitive information or perpetuate biases. Example: avoiding the disclosure of personal details in explanations for automated hiring decisions. Everyday example: imagine an AI powered virtual assistant that suggests personalized movie recommendations. XAI would involve the assistant explaining why a particular movie was recommended, perhaps highlighting specific genres, actors, or user preferences. This transparency helps user understanding and trust the recommendation, making the artificial intelligence system more user friendly and accountable. Artificial intelligence bias and fairness. Artificial intelligence bias and fairness address the challenges associated with biases in data and algorithms, ensuring that machine learning systems are fair and do not discriminate against certain individuals or groups. Here is a detailed exploration of artificial intelligence bias and fairness. Bias in data definition: unintended and systematic errors in training data that can reflect existing societal biases. Example: if historical hiring data is biased towards a specific gender, the model may learn to perpetuate gender imbalances. Algorithmic bias definition: biases introduced during the development of algorithms leading to discriminatory outcomes. Example: a facial recognition system that performs better for lighter skinned individuals, leading to misidentification for darker skinned individuals. Fairness definition: establishing criteria and matrices to define fairness in machine learning models. Example, different definitions of fairness such as demographic parity or equalized odds depending on the context. Mitigation strategies. Definition, techniques and approaches to identify and mitigate biases in both data and algorithms. Example, resampling techniques to balance underrepresented groups in training data. Explainability and accountability. Definition, ensuring that artificial intelligence systems are transparent in their decision-making processes and developers are accountable for addressing biases. Example, providing explanations for model predictions and holding developers responsible for addressing identified biases. Diversity in development teams. Definition, encouraging diverse perspectives in the teams developing artificial intelligence systems to avoid unintentional biases. Example, a team with members from different backgrounds is more likely to identify and address diverse forms of bias. Continuous monitoring. Definition, regularly monitoring model performance and updating algorithms to address emerging biases. Example, periodically re-evaluating and retraining a predictive policing model to avoid reinforcing biased patterns. Ethical considerations. Definition, considering the ethical implications of artificial intelligence technologies and their impact on individuals and society. Example, evaluating whether an artificial intelligence system could disproportionately impact vulnerable populations. Everyday example, imagine an AI-driven loan approval system. Artificial intelligence bias and fairness would involve scrutinizing the training data to ensure it is representative of diverse applicants. Mitigation strategies might include adjusting the model to prevent biased outcomes, ensuring that individuals from different demographics are treated fairly in the loan approval process. The goal is to build artificial intelligence systems that avoid perpetuating and amplifying existing societal biases. Artificial intelligence and robotics. Artificial intelligence and robotics involve the integration of artificial intelligence technologies into robotics systems, enhancing their capabilities, autonomy, and adaptability. Here is a detailed exploration of artificial intelligence and robotics. Autonomous navigation. Definition, enabling robots to navigate and move in their environment without continuous human intervention. Example, autonomous drones using artificial intelligence to navigate through obstacles in real time. Machine learning in robotics. Definition, implementing machine learning algorithms to enable robots to learn from data and improve their performance. Example, a robot learning to grasp objects of varying shapes and sizes through reinforcement learning. Computer vision in robotics. Definition, utilizing computer vision technologies to enable robots to interpret and understand visual information. Example, robots using vision systems to identify and pick objects in a warehouse. Collaborative robots, COBOTS, cobots. Definition, robots designed to work alongside humans, collaborating on tasks in shared workspaces. Example, cobots assisting workers on an assembly line by handling repetitive or heavy tasks. Sensor fusion. Definition, integrating data from multiple sensors to provide robots with a more comprehensive understanding of their environment. Example, robots combining data from cameras, LiDAR, and tactile sensors for improved perception. Adaptive learning. Definition, allowing robots to adapt and optimize their behavior based on changing conditions or new information. Example, industrial robots adjusting their movements to accommodate variations in the production environment. Human-robot interaction. Definition, enhancing the ability of robots to understand and respond to human gestures, speech, and actions. Example, social robots capable of engaging in conversations and understanding emotional cues. Everyday example. Consider a household cleaning robot equipped with artificial intelligence and robotics. This robot can autonomously navigate through rooms, avoiding obstacles, and adapt its cleaning strategy based on the layout of the space. It utilizes computer vision to identify areas that require cleaning and learns from its experiences to optimize future cleaning tasks. The integration of artificial intelligence in robotics transforms the robot into an intelligent and adaptive assistant in daily chores. Artificial intelligence in healthcare. Artificial intelligence in healthcare involves the application of artificial intelligence technologies to enhance medical diagnosis, treatment, and overall healthcare delivery. Here is an in depth exploration of artificial intelligence in healthcare, medical imaging, and diagnostics. Definition: using artificial intelligence algorithms to analyze medical images such as X rays, MRIs, and CT scans for accurate and rapid diagnosis. Example: artificial intelligence assisting radiologists in identifying abnormalities in medical images. Predictive analytics. Definition: employing AI models to predict patient outcomes, disease progression, and potential health risks. Example: predicting the likelihood of readmission for patients with chronic conditions. Personalized medicine. Definition: tailoring medical treatment plans based on an individual's genetic, molecular, and clinical data. Example: customizing cancer treatments based on the genetic profile of the tumor. Virtual healthcare assistants. Definition: AI powered virtual assistants providing information scheduling appointments and offering health advice. Example: virtual assistants helping patients manage medications and follow treatment plans. Drug discovery and development. Definition: utilizing artificial intelligence to analyze biological data and accelerate the drug discovery process. Example: identifying potential drug candidates by analyzing large data sets of molecular interactions. Remote patient monitoring. Definition: using artificial intelligence to remotely monitor patients' health conditions and alerting healthcare providers to potential issues. Example: wearable devices tracking vital signs and sending real-time data to healthcare professionals. Natural language processing in healthcare. Definition: applying NLP to extract valuable insights from unstructured healthcare data, such as clinical notes and research papers. Example: analyzing electronic health records for patterns and trends using NLP. Robot assisted surgery. Definition: integrating artificial intelligence into surgical robots to enhance precision and improve surgical outcomes. Example: surgical robots guided by artificial intelligence algorithms for minimally invasive procedures. Everyday example: imagine a diabetic patient using a continuous glucose monitoring system with artificial intelligence capabilities. The system predicts blood glucose levels, providing timely alerts and personalized recommendations for insulin dosage adjustments. Artificial intelligence in healthcare not only aids in managing chronic conditions but also contributes to more efficient and personalized medical care. Artificial intelligence in finance. Artificial intelligence in finance involves leveraging artificial intelligence technologies to enhance financial analysis, decision making, and various aspects of the financial industry. Here is a comprehensive exploration of artificial intelligence in finance. Algorithmic trading. Definition: using artificial intelligence algorithms to automate trading strategies, analyze market conditions, and execute trades. Example: high frequency trading systems making split second decision based on market data. Fraud detection and prevention. Definition: employing artificial intelligence models to identify and prevent fraudulent activities in financial transactions. Example: artificial intelligence algorithms analyzing patterns to detect unusual spending behavior on credit cards, credit scoring and risk assessment. Definition: utilizing artificial intelligence to assess credit worthiness and predict the risk associated with loans and financial transactions. Example: artificial intelligence models analyzing various factors to determine an individual's credit score. Customer service and chatbots. Definition: implementing artificial intelligence powered chatbots for customer interactions, query resolution, and personalized financial advice. Example: virtual assistants assisting customers with account inquiries and transaction details. Personal finance management. Definition: developing artificial intelligence based tools to help individuals manage budgets, investments, and financial goals. Example: artificial intelligence driven apps providing insights into spending habits and suggesting budget adjustments. Sentiment analysis in trading. Definition: analyzing social media and news sentiment to predict market trends and make informed trading decisions. Example: artificial intelligence algorithms assessing public sentiment to anticipate stock market movements. Robo-advisors. Definition: implementing artificial intelligence driven platforms for automated financial planning, investment advice, and portfolio management. Example: robo-advisors creating diversified investment portfolios based on individual risk tolerance and financial goals. Blockchain and cryptocurrency analysis. Definition: utilizing artificial intelligence to analyze blockchain data and predict trends in cryptocurrency markets. Example: artificial intelligence algorithms identifying potential market trends by analyzing patterns in cryptocurrency transactions. Everyday example: consider an individual using a mobile banking app that incorporates artificial intelligence in finance. The app provides real-time spending insights, suggests budget allocations, and recommends investment opportunities based on the user's financial profile. Artificial intelligence-driven financial tools contribute to more personalized and informed financial decision-making for individuals. Artificial intelligence for business. Artificial intelligence for business involves integrating artificial intelligence technologies into organizational strategies to enhance efficiency, decision making, and overall business operations. Here is a comprehensive exploration of artificial intelligence for business. Operational automation. Definition: using artificial intelligence to automate routine and repetitive tasks, streamlining business processes. Example: implementing robotic process automation (RPA) for data entry and administrative tasks. Predictive analytics. Definition: leveraging AI models to analyze historical data and make predictions for future trends and outcomes. Example: forecasting sales trends based on past data to optimize inventory management. Customer relationship management (CRM). Definition: implementing artificial intelligence in CRM systems to enhance customer interactions, personalized marketing, and customer service. Example: artificial intelligence driven chatbots providing instant customer support and recommendations. Supply chain optimization. Definition: using artificial intelligence to optimize supply chain operations, inventory management, and demand forecasting. Example: artificial intelligence algorithms predicting demand fluctuations to optimize inventory levels. Human resources management. Definition: applying artificial intelligence in HR processes for recruitment, employee engagement, and talent management. Example: artificial intelligence driven tools screening resumes and predicting candidates' suitability for specific roles. Business intelligence and decision support. Definition: utilizing artificial intelligence for data analysis and providing actionable insights to support strategic decision making. Example: artificial intelligence systems analyzing market trends to inform product development and marketing strategies. Fraud detection. Definition: implementing artificial intelligence to detect and prevent fraudulent activities in financial transactions and business operations. Example: artificial intelligence algorithms analyzing transaction patterns to identify potentially fraudulent activities. Smart personalization definition tailoring products, services, and user experiences based on individual preferences using artificial intelligence. Example: e commerce platforms recommending products based on past purchases and browsing history. Everyday example: consider a retail business implementing artificial intelligence for business. The business uses artificial intelligence to automate inventory management, predicting customer demand and ensuring optimal stock levels. Artificial intelligence driven CRM tools provide personalized recommendations to customers, enhancing the shopping experience. Overall, artificial intelligence contributes to operational efficiency and customer satisfaction, driving the business success.